All right, so this is section 5.2 about power and polynomial functions. And so let's define those things first. The power function is just a function. It's got a single term that's a product of a real number coefficient and a variable that's raised to a power that is also a real number. And so your general format for that is k to the xp, where k is the coefficient, p is the power. So some functions that are power functions, the constant function, a single term, linear function, a single term quadratic, 1 over x because it can be written as x to the negative 1, 1 over x squared because it can be written as x to the negative second power, root of x, it can be written as x to the 1/2 power, and cubed root can be written as x to the 1/3. So all of these can be written in this format where it's some number times x to some power. And so these are power functions. And so these are not power functions over here. So this is because this is a rational function. It's got multiple terms and can be written as a single fraction, but it's got these multiple terms. So you can't write it as a single term, even if you were to make those negative powers. These cannot be combined. So this one is 2 terms, and a power function has to have 1 term. So that one's not because it's rational. This one is because it has 2 terms. And this one is because the power is a variable, and it has to be an actual number. And so this third one's called an exponential, and that's not a power function. So which of these are power functions? So f of x can be written as 8x to the 4th, so that is a power function. This cannot be written as a single power because we can't combine these terms, so this is not a power function. And then this last one is also not a power function because it's just like the other rational function we saw that you can't write as a single term that's not in a fraction. All right, so now a polynomial function is some function that's either just 0 or is the sum of a limited number of non-zero terms. So each of those being a coefficient with a variable raised to a non-integer power. So this is the algebraic definition. And then, of course, the leading coefficient can't be 0. So for example 1, which of these are a polynomial function? And so the first, if we simplify all this, it would just be 6x to the 4th plus 4. This is a polynomial. This one would be negative x cubed plus 4x, also a polynomial. This one is not a polynomial, and that's because it has a power in it that is applied to an expression that can't be expanded, right? So we would have to have whole number exponents for a polynomial, and that's one of the differences between power and polynomial. You cannot have these fractional exponents in a polynomial function. So the next thing we want to talk about is identifying end behavior of these types of functions. And so end behavior is basically what is happening on each end of the graph, and specifically, what y value vertically does a function approach as the x values get really, really big in the positive direction or really, really big in the negative direction. And we can look at the graph to determine the end behavior, or we can examine the degree and the leading coefficient. So some more vocabulary. The degree of a polynomial is the largest exponent. And we'll see later that even degrees have different end behavior than odd degrees. And the leading coefficient of a polynomial function is just the coefficient of the variable with the highest power. So some important things when you're looking at even powered functions, so like square to the 4th to the 6th, these functions have end behaviors that do the same thing, right? They either both go up, like in this case, or they both go down. Now, an odd power function has one end going up and the other end going down, and it can be vice versa. And so the way we denote end behavior is with this terminology. So as x approaches negative infinity, that's go on the left-hand side. Y is, for this graph, also approaching positive infinity. It's indefinitely going up. And then on the right side of this even power function graph, as x approaches positive infinity, which is moving to the right, y is also approaching positive infinity. So for this odd power graph here, as x approaches negative infinity, as we go this way on the x-axis, our vertical component of the graph is moving down to negative infinity. And as x approaches positive infinity, here we are also approaching positive infinity in the y direction. So again, this is the left side of that graph, and this is the right side of the graph. And so to determine end behavior given a graph, we're just going to look at the graph. And so I'm going to draw in black what you write every single time when you're addressing end behaviors. So that would be as x approaches negative infinity, y approaches, and you're going to put something here. And so for this one, we would say, okay, as x approaches negative infinity, y is approaching positive infinity. And so the red is what changes every time. So this would be as x approaches positive infinity, y approaches, again, positive infinity. So in red is what you'll change each time. And the black is kind of your template for writing the end behavior of a function. And so let's look now in figure 6 at an odd function. And so this would be as x approaches negative infinity, y approaches, something. And that something on the left is going to be positive infinity, because on the left side of the graph, it is going up. And so the other side would be as x approaches positive infinity. That's the right side of the graph. Y is actually going down. So that's going to be negative infinity for the y component. Now, we can also determine end behavior given a function. And to do that, we're going to examine the leading coefficient and the degree. And so first thing I'm going to do every single time is I'm going to say, okay, what is the sign of the leading coefficient? And I'm going to say, what is the degree of the function? And knowing these things, I'm going to be able to figure out the end behavior. So the leading coefficient is 2, and it's positive. So the leading coefficient is positive, and the largest exponent is a 2. And so that is an even number. And so from this, we can say, okay, the sign of the leading coefficient tells me what it does on the right. So on the right, it's going up because that's positive. And then the degree is going to tell me what happens on, the left. And what that means is if it's even, it does the same as the right, like it does here. And if it's odd, it's going to just do what's different. So let's look here real quick. So again, let's examine the sign of the leading coefficient and the degree. This is still a degree 2 polynomial, except now it's a negative leading coefficient. So again, leading coefficient says on the right, this is going to be going down now because that's negative. It is again an even degree, so on the left it's going to do the same thing. And so kind of once you get a handle on what that's doing, you can actually write the end behavior. So as x approaches negative infinity and as x approaches positive infinity, so y is approaching on the left, it's approaching infinity because it's going up. And so that comes from here. This is on the left. And as x approaches positive infinity on the right, we also indicated that it was going up. And so that is positive infinity. And that is from here. Okay. So again, let's write the end behavior in notation down here. So again, our template, as x approaches negative infinity, y approaches something. And as x approaches positive infinity, y approaches something. And let's go back and fill in the buttons for what that is. So remember that this is the left in behavior and this is the right, because as we go left, it's negative, and as we go right, it's positive. And so it looks like both of these are going down. So on the right, we're going down, that's negative infinity. On the left, we're also going down, so that's negative infinity. Let's do a couple more. These are a little bit different, but we're going to kind of approach it the same way. So what is the sign of the leading coefficient in the degree? I'll start abbreviating. And what is the sign of the leading coefficient in the degree? So the sign of the leading coefficient here is positive, here it's negative, and they're both degree 3 functions. And so 3 is an odd number. So again, the leading coefficient determines that on the right, we're going up because it's positive. And because it's odd, though, on the left, we're just going to do the opposite thing instead of the same thing like we do when we're even. So here on the right-hand side, this is negative, so we're going down, and an odd degree indicates different behavior, so that's going to go up. And again, as x approaches negative infinity, as x approaches positive infinity, y is going to approach something. And filling that in, we'll see that on the right, which is positive, we are going up, which is positive infinity. And on the left, we are going down, which is negative infinity. Again, just recalling that this is the left-hand side and this is the right-hand side. And so to write the behavior down here, we'll write as x approaches negative infinity, y approaches, remember that's the left, up is positive infinity. As x approaches positive infinity, y is going down because that's on the right. So again, just remembering that this is right and this is left, and we'll just match those things up. In short, the sign of the leading coefficient determines if the right-hand behavior is going up or down, and the degree is going to determine if the left is doing the same thing or the opposite thing. So now we want to talk about local behavior of polynomials, and what that means is instead of just on the ends, we're also interested in what happens kind of in the middle of the function. And so we have a couple of vocab words. The first, we'll start down here. We know what the intercepts are. They're just the y and x intercepts on the graph. So here are the x-intercepts, and here is the y-intercept. But this new thing is called a turning point, and it's just where a function changes from increasing, decreasing, or hills or valleys. So here's a turning point, and here's a turning point. So we're interested in those things. So determining the intercepts of the polynomial. And this is the same thing as we've been doing. Y-intercepts are evaluating the function at 0, and the x-intercepts are where the function itself is equal to 0. So f of 0 for our y-intercepts, that would be 0 minus 2 times 0 plus 1 times negative 4, which is essentially going to be negative 2 times 1 times negative 4, which is going to be positive 8. And so the y-intercept is at y equals 8. Done. So the x-intercepts are where the entire function is equal to 0. And so we set the entire thing equal to 0. And you'll notice that this has already been fully factored for us. And so we can just set each factor equal to 0, and we'll have x equals 2, x equals negative 1, and x equals 4. And these are all of our x-intercepts. So nothing new there. Let me highlight all of this. So this is a y-intercept, and your x-intercepts are here. So determining, again, the intercepts, if it's not already factored, you will have to factor it. And so recall that if you have this x to the fourth minus 4x squared minus 45, you use the same factoring method, basically almost as if it was a normal quadratic, right? This is called a quartic. And we use the same factoring as the quadratic. So in other words, I'm looking for two numbers who multiply to negative 45 and who add to negative 4. And so, I'm going to be looking at 5 and 9. And so one of these needs to be negative. I'm going to make it the 9 because then the sum will be negative. And so I can rewrite this as f of x equals x to the fourth plus 5x squared minus 9x squared minus 45. And then we're going to factor by grouping. We're going to take the GCF of the first two terms. That'll be x squared, leaving x squared plus 5. And then I'm going to take the GCF of the second terms, which will be negative 5. That'll be x squared plus 5. And then finally, fully factored, this will be x squared plus 5. X squared, well, not fully factored, almost. Factoring that difference of squares will give me x squared plus 5, and then x plus 3, x minus 3. And now that that's done, we can just set each factor equal to 0, because that's what we should do to find our intercepts. And so x squared plus 5, you're going to end up with plus or minus the square root of negative 5. And we know that that is not a real number. These are imaginary numbers. Can't take the square root of a negative number. So this gives you no x-intercept from here. And then, of course, these other two, I'll have x equals negative 3 and x equals 3. And these are actually my x-intercept. And we'll make a note here that these are not good because they're imaginary. So they're roots, but they never cross the x-axis. So they're not an x-intercept. And so your x-intercepts are here. And of course, to find the y-intercepts, we're just going to evaluate f of 0, which in this case would just be negative 45. So this is my y-intercept here. All right, so why don't you give one of these a try? So given the polynomial function shown, go ahead and find the x and y intercepts. I'm going to pause the video and come back to see how you did. That is definitely a good idea. So if you paused, the y-intercept is y equals 0. And the x-intercepts for this function are going to be x equals 0, x equals negative 2, and x equals 5. The next thing is we're going to compute. Yeah, it's the end of the day. We're going to compare smooth and continuous graphs. And so a couple of new words. All polynomial functions have graphs that are smooth and continuous. And so a continuous function is a function that has no break in its graph. In other words, you can draw it without lifting your pencil. And a smooth curve has no sharp corners. And so in short, polynomials are like this instead of like, say, that with that sharp corner. That's no, like the smooth curve doesn't have any of that. And so the key piece of information here is a polynomial of degree n will always have at most n x-intercepts and n minus 1 turning points. And so what I want you to do here is, just tell me the number of turning points and intercepts. Of this polynomial. So this is pretty simple. What is the degree, which is n? Well, the largest exponent is 10. So at most, we have 10 x-intercepts and n minus 1, or 9, turning points. Okay, you want to try this one and pause the video and come back, see how you do. So the max number of x-intercepts and for this guy is 12, and the max number of turns is going to be 11. All right, so last thing is drawing conclusions about a polynomial function just looking at the graph. And what I want you to do is I want you to tell me what you can about the degree of this polynomial based off of this. So I want to first examine the number of turning points and the number of x-intercepts, right? So I have x-intercepts, I have 1, 2 of those, and I have 1, 2, 3 turning points. And then I also know that because the end behavior is the same, that this is going to be an even function. And so I know that the degree is even. And at least 4. Well, it has to be at least 3 because I have 3 turning points, but it's even. So the next possible number that's even is 4. So that's how I know that it's at least 4. And that's what I want you to tell me. So now you try. Examine the x-intercepts and turning points and let me know what the degree, the parity, is it even or odd, and what its lowest number could be. All right, so here the degree is odd and at least 3. Right, and then finally, not looking at a graph anymore, let's draw conclusions about the number of x-intercepts and turning points looking at the function. So ultimately what I want to know is x-intercepts and the turning points of this graph. And so the degree of this polynomial is 3 because it has 3 x's. So if we multiplied this out, you would see an x cubed as the largest degree. And so the degree is 3. So that means at most, and we can't say for sure, but at most 3 x-intercepts and 2 turning points, right? So it could have less than that, but at most it will have this many. Okay, so you give it a try and tell me the at most the amount of x-intercepts and turning points that this function in the you try could have. All right, so this is at most 3 x-intercepts and 2 turning points as well. So I hope that was helpful. Take a look at the 5.2 exercises. This will be on your midterm next Wednesday, but not on your quiz on Monday. But do go ahead and start working on the practice problems. You'll see those in the normal location. So I will see you guys soon.